an organization that is trying to figure out how to use machine learning techniques to actually promote and act on the impacts of climate change. So thank you, and we're looking forward to another great talk.
All right, thanks so much. So I think kind of, underlying all of the talks in this session is this realization, right, that climate change is one of the most pressing issues that we as a society are facing today. And we're going to need an all-hands-on-deck approach to address this, kind of leveraging all of the tools and approaches we have across society. AI is one of those tools, not a silver bullet certainly, but something that can be useful across a bunch of different climate change related applications. And we've heard about several examples throughout the session, and I want to try to provide a quick overview of the landscape of applications as they exist. So several years ago, a group of collaborators and I put out this paper called Tackling Climate Change with Machine Learning. And in this paper, we tried to do an assessment of, where is it across, reducing greenhouse gas emissions and adapting to the effects of a changing climate, where is it that machine learning can play a role? And we looked at applications across, for example, the electric power sector, heavy industry, climate science, health systems, and so forth. For those who are interested in this area, I'd encourage you to check out the paper, and I'm certainly not going to be able to go through kind of all of the applications today, but what I want to try to provide is a quick overview of kind of cross-cutting themes that came up in this paper. So the first we heard about is distilling raw data into actionable information. So things like taking satellite imagery and turning it into information about where greenhouse gas emissions are coming from, or what are the crop types on agricultural land, or what are the energy efficiency characteristics of buildings in order to help us make more targeted decisions. We also see applications in forecasting taking, as we heard about, different streams of data like weather data, historical time series data, and images of things like clouds moving overhead to improve our predictions of, for example, near-term solar power output. And this theme comes up across things like also the use of generative AI for precipitation forecasting in the near term to allow us to come up with probabilistic predictions for precipitation. We also see uses of machine learning in helping us to actually improve the efficiency of real-world operational systems, things like controlling heating and cooling systems in buildings or in data centers in order to help them achieve their objectives of, for example, maintaining thermal comfort or keeping equipment sufficiently cool while kind of improving the efficiency of their operation. And similarly, we see applications where machine learning has helped to actually detect inefficiencies in operational equipment, things like switching infrastructure in trains, in order to try to fix faults before they occur or shortly afterwards. And then we also see, in addition to the use of machine learning in operational systems, we see its capabilities in accelerating scientific experimentation. So we've heard about applications in, for example, next-generation materials discovery. And we've also heard about applications in things like machine learning being used to approximate parts of time-intensive simulations like subgrid parameterizations in climate models. So this is sort of, a taxonomy one can use to think about what are the different ways that machine learning can play a role. And again, we've heard a lot of, I think, really important points from previous speakers about the fact that, machine learning, not a silver bullet. Where it's used, it's often part of one larger solution. So if you predict a material, you actually need to synthesize it. It's very important as a result to do this work in collaboration with stakeholders, with a kind of pathway to deployment in mind, in order to understand how does a machine learning-based component of a broader climate solution actually get actualized, and how do you actually need to adjust the way you do the machine learning in the first place to make that actually happen. Now, the applications I talked about on the previous slide, they contain a combination of things that can be implemented with out-of-the-box machine learning methods, but they're also places where we need innovation in the machine learning methods themselves. So, for example, my own work looks at the use of machine learning in the electric power sector, which contributes about 1/4 of global greenhouse gas emissions, and where decarbonizing power grids is going to require radically rethinking how we actually manage them by integrating renewables, by enabling distributed devices to act more flexibly on power grids, and so forth. Machine learning has been proposed for use to do this, to help us more effectively optimize and control power grids. But the challenge is that machine learning methods, as we've heard about before, can fail, and potentially catastrophically. And if you're using a machine learning method to manage a power grid, and that fails, that can mean large-scale blackouts, loss of lives, things that we're fundamentally not willing to accept as a society as a type of failure. So to dive into that, When we think about electric power grids, we're talking about the systems through which our electricity is produced, then transported along lines and electrical equipment, and then consumed by end-use consumers like us. These systems are governed by various sorts of physics, so when you put power into the power grid, that power flows along the lines and electrical equipment according to physical rules. There are various hard constraints, things like I need to maintain some kind of electrical equilibrium, or I can only modulate my equipment by a certain amount from moment to moment. And also various decision-making procedures that run on top of this. So how do I actually, for example, schedule power subject to uncertain demand in order to minimize, satisfy some objective like satisfying demand and minimizing costs. These problems are traditionally dealt with by kind of traditional optimization and control algorithms where you actually write down a set of rules that govern how the system behaves and solve over them. And the great thing is that the kind of decisions that you get out on the other side do satisfy the physics and hard constraints you care about, but optimization and control algorithms are really struggling to scale to meet the kind of demands that are kind of brought about by integrating renewables and distributed devices at scale into the grid. Machine learning has the strength that it can ingest large amounts of information and use that to make decisions fairly quickly, but machine learning methods have no notion of satisfying physics and hard constraints, which is really terrible for applications like this. So what my work looks at is how do we combine these two worlds? How do we kind of get the benefits of optimization and control in terms of actually satisfying physics and hard constraints, but how do we leverage the kind of ability of machine learning to make dynamic, nuanced, and well-performing decisions based on large amounts of data? And so my work proposes a framework called optimization in the loop machine learning, which basically says if we have a machine learning model, for example, a deep neural network, can we actually write down the physics and hard constraints that we care about and actually embed those as, for example, layers within our neural network that enforce the neural network's output to satisfy some kind of property like satisfying physical constraints on a power grid? And this paradigm plays out in a lot of different ways. So some of my work has looked at using this to come up with electricity demand forecasts that avoid making catastrophic mistakes that are, bad for the person who would use those forecasts to schedule power. And we see things like a 40% improvement in kind of power scheduling costs when you use this kind of decision-cognizant, physics-cognizant algorithm. Some of my work has also looked at, given that we have all of these large-scale optimization problems on power grids today that are infeasible to run, can we use machine learning to approximate these optimization problems, but in ways that preserve the physical constraints within those optimization problems that we need to satisfy? And some of our preliminary work has seen, things like we're able to use machine learning algorithms to speed up power system optimization problems by a factor of 10, while still actually making sure to satisfy the physical constraints internally and achieve good performance in terms of the objective of the optimization problem. And we can still, use this optimization in the loop machine learning paradigm to actually come up with controllers for different devices on power grids that perform well, but still have kind of provable robustness guarantees even if something goes wrong in the underlying system. For example, in some preliminary experiments, we've seen the ability basically to combine reinforcement learning and kind of control theory in order to construct hybrid controllers using this optimization in the loop methodology that basically improve control performance by an order of magnitude over traditional robust control methods while still provably satisfying the same physical guarantees that control theory would. The kind of overall vision represented by this is basically that if we want to leverage machine learning in safety-critical systems, like power systems, like certain aspects of buildings, like heavy industry, that are of relevance to climate change, we really need to make sure that machine learning methods have the kind of guarantees and physical knowledge internally that is necessary to make sure that we don't, see catastrophic failures occur. And we can do this not by throwing away all of the research on engineering, on physics that has been done in those fields, but really figuring out clever ways to merge machine learning-based approaches with these past approaches that we have. So in the last few minutes, what I want to emphasize is that while my talk so far, while the talks of the other speakers have really focused on ways that machine learning can really be a force multiplier for climate action, machine learning is a general purpose tool which has a really nuanced and complicated relation with climate change overall. For example, machine learning is used to accelerate emissions-intensive industries and processes in a way that invariably makes climate change worse. Things like generating, hundreds of billions of dollars of revenue for the oil and gas industry by facilitating exploration and extraction of natural resources, or facilitating internets of cows, which make cattle farming more productive. Machine learning also has various system-level impacts that we don't always think of as directly relevant to climate change, but are. Things like machine learning as a primary driver of targeted advertising, which invariably change how we consume without necessarily always making us happier, but in a way that does have implications for greenhouse gas emissions. And machine learning as a driver of technologies like autonomous vehicles, which will certainly change how our transportation sector looks, but where, depending on how those are developed, that can be good or bad for climate, depending on whether they, for example, entrench private fossil fuel transportation or enable us to transition to multimodal, low-carbon transportation. And then last but not least, I think particularly salient as we think about generative AI, machine learning methods themselves have a computational and hardware footprint. The electricity consumed by the computations they run, the water and needs associated with kind of cooling data centers, the materials associated with hardware. And these impacts come both when actually developing machine learning methods and using them in the real world, and as we start to see large amounts of deployment and use of methods like chatbots, we really do have to think about this pocket of emissions as something we really need to address. Some of my work has looked at this in the kind of realm of policy. So how can we engage policymakers to enable them to both enable those applications of machine learning that can be beneficial to climate action, but also how do we enable policymakers to more broadly think about business as usual machine learning applications and how we align those with climate action. Both of these things, ML for climate, but aligning ML more broadly with climate, are essential to really thinking about climate. And so I hope that the discussion of health of the planet isn't confined just to today's session, but is something that comes up as we reimagine generative AI as a whole. How do we do this in a way across different applications that are really in line with climate change goals? And for those who are interested in engaging with this topic further, I would encourage you to check out Climate Change AI as a community, where you can find resources, workshops to share your work, summer schools, funding, webinars, policy-related work, and many other ways to engage. So with that, thanks so much, and I, in the last few minutes, welcome any questions.
I have a question with regards to your grid balancing algorithms, where you said you have the machine learning part and you have the constraints part. I'm curious what type of data you wish you would have that's currently not available and should be collected to make either of the two parts more strong.
That's a great question. So in terms of the kinds of data needed, I would say that, for example, a lot of my work really looks at how do you, in some sense, in theory, create a machine learning algorithm that approximates a grid optimization problem, often that comes from a textbook formulation. But in reality, power system operators, for example, are dealing with, changing grid structures, or changing with different kinds of physical constraints that aren't written down in the textbooks, and so forth. And so I think some of the things that are needed are literal raw data that is coming from sensors or that describes how the grid is changing. But some of it is, in some sense, sort of human capital and knowledge transfer, and kind of making that publicly available so that more people, you don't have to have just the few people who have access to the institutional structures to set up a bilateral collaboration with a power system operator to kind of get some of this knowledge. We need ways to kind of more broadly share how is it that the grid is in reality looking now? How do we externalize these problems through kind of challenges, through benchmarks, through other kinds of data sets to allow more people to contribute?